We can start early, right?
Can we?
No, we can't, but I can start writing on the board.
You're a professor. You can do
So we did this. Oh, well, you know what? We did not do. Well, yeah, we did. Yeah.
You did infinity minus infinity.
We did?
Yeah, it's covered on homework.
On the homework, yes, but not in class. So I'm going to start with that.
Oh.
Okay. Wow, these markers are terrible.
Yeah, that's one I didn't understand what's bounded.
Let's see.
Square root.
Which one? Like this? Yeah.
Square root, right? It was on the one that was.
Yeah, I did do homework problems like that. Anybody who came in just now, I have your quizzes up here. You can just come and grab them if you want them, or you can wait till after class. All right, let's get started. Last time, I hope you had a good holiday weekend, by the way.
Well, me and you didn't die yet, so.
Yeah, we're all here, I guess. That's good. Normally, you know, I start out Monday, Wednesday class. I have a Cal 1 class on a Monday, Wednesday at 11 o'clock. So this has always been the second, every time I've come in here, it's been the second time I've talked about this material, okay? But now we flip-flop. So this will be the first time I'm covering 2.1. Just so you know, there's another set of class lecture videos out there from my other class. If you ever want to go watch them, you can. But we won't be ahead of this class anymore. So. All right, so now last time we talked about all of these scenarios. We know that if we see 0 over 0, we have to do some sort of algebra or trick. Infinity over infinity, we have to do some sort of algebra or some sort of trick. Fixed over infinity, 0. Fixed over 0,
Negative infinity to infinity.
either negative infinity, positive infinity, or does not exist. So this was the three cases. What I did not get to finish up, and what we're going to do today is, what do you do when you see something like this, where you have something bounded over infinity, and we have not looked at infinity minus infinity. If you did the homework, and you looked at the homework solutions, I actually did these, but since I didn't talk about them in class, I will address those. So let's first talk about this bounded over infinity. Oh, and then we're going to do 2.1. All right, so bounded over infinity. First, let's understand what I mean by bounded. When you take a function, let's say for example the function f of x equals sine x, which is a very simple function. We know that when you graph it, it looks like that, goes back that way. And we would say that this function is bounded. And that, pardon?
Are the only ones bounded or trig functions? Or?
Oh no, you can have functions that are bounded that are not trig functions. Yeah. Yeah, anything where you'd have an asymptote where you can't go above it, something. Yeah, they're not the only ones. But these are the ones we see a lot in Cal 1. So this is bounded because we know this inequality is true, that sine x is always between 1 and -1. So it's bounded. It's stuck between two values, right? It's never going to get bigger than 1. It's never going to be less than -1. So that's what, when we say bounded, we're talking about a function like this. Cosine would be the same way. How about tangent? Is tangent bounded? No, tangent's not bounded. Yeah, but even in its domain, it becomes infinite, so it would not be bounded. How about cotangent?
Yes.
Cotangent is bounded. If you remember what cotangent looks like, what is it? It's like, it's either this one or this one, right?
I think it's that.
You have this on your formula sheet. Go back and review these if you need to. All right? But there is a bound on these. So anyways, all right, let's move on. The idea here is that if we have something that's bounded on top, right, if you take a limit and you have bounded on top, and you have something that's becoming infinite on the bottom, that this will always go to 0. Okay? Just like fixed over 0 did it, right? Fixed over infinity went to 0. Bounded over infinity goes to 0 also. So an example of this would be limit, let's say x goes to infinity of cosine x plus 2 over x squared plus 1. So we'll look at this. We let x go to infinity. Of course, the denominator is going to infinity, right? The numerator, though, is not going to infinity. It's not going to 0. It's oscillating back and forth. This is the cosine function. It's been shifted up 2. But it's still bounded, isn't it? You could, if you want, write out the inequality like this. We know cosine x is between -1 and 1. We have cosine x plus 2, so if we add 2 here, add 2 here, add 2 here, okay, then you would get a new inequality that would read what? -1 plus 2, 1 less than or equal to cosine x plus 2 less than or equal to 3. And so this numerator is bounded, isn't it? And there's no work that needs to be done. As soon as we see that it's bounded, we write down the answer, 0. All right? Now, the reason why it's doing it, so this is 0. The reason why it's doing it is because if you graph it, did I show y'all at the end of class something? I think I did, but y'all were ready for the weekend. Sine x over x, I think I did that one. Does that look familiar or no? Yeah. That right there, I tried to convince you, is bounded over infinity. You agree? But if we try and look at this a different way and write the x in the denominator as a 1 over x out front, and go back to pre-cal and remember that when you had something like a sine x, the a was the amplitude. That was how tall the sine curve was. And a was always a constant. So if this a was a 3, then you would know your sine curve was between -3 and +3. But if the a, right, if the a out here is not a constant, you look at this as the a, as x gets bigger, this thing is going to 0, isn't it? So it's almost like you're trying to draw the sine curve, but as you go out, your amplitude gets smaller and smaller and smaller. So it would look something like, well, at 0 it's undefined, so I can't do that. Well, actually, can you tell me what this function does close to 0? What does that function do as you get close to 0? If I change this to limit x goes to 0 of this, 1. Do you remember that? That was one of those ones you had to remember? Yes? So I know at 0, if I were to start drawing this, this would not be defined. I would have a hole here, but it would be close to 1, wouldn't it? Does it come in this way? And same with the other side. But so to the right, as I start to draw it, I start to draw the sine curve, but with a amplitude that's getting smaller. So as I go down here, the amplitude gets smaller and smaller and smaller and smaller and smaller. And it's headed towards 0. Now, it's passing through 0 over and over and over, isn't it? But every time you move to the right, it's like you can almost look at it like a window that's closing in, right? It's like closing in on it, and it's squeezing it down shorter and shorter, and it goes to 0. The reason I say that it passes through 0 is because up to this point, we've never had a limit approach 0 and actually achieve that value at some places. We've always had like a horizontal asymptote, like a rational function that does something more like this, gets closer to 0 without actually getting there. This one actually passes through it but it's just that that amplitude keeps shrinking as it goes. Does that make sense? Now, another one I could do here is something like this. Now, we haven't talked about it, the exponential functions. We are going to talk about them. But e to the x is another example. That would also go to 0, right? Because your top is bounded. And your denominator, well, e is like 2.7 something raised to an infinite power is going to get huge. So that's also going to do the same thing and shrink it down. How do you think it would look compared to the previous one? You think it would shrink down faster or slower? Faster, much faster, exponentially. Like the other one was shrinking down, but it was linear, right? Because it was just x down here. So the bottom was growing when it was x. It was growing, but it was growing linearly. This is growing exponentially. So you would have a very rapid decline of that sine curve. In fact, it would look like this. This is a way you can do it. It's really actually cool. Y'all know what e to the x looks like? No? E to the x looks like this. That's e to the x. Okay? But if I move it out front and write it like this, 1 over e to the x times sine x, that's actually what it is, right? 1 over it. So if you do 1 over this, it actually like flips it and it becomes the exponential function going this way, like this. Right? That's what will happen. And if I draw another one reflected over the y-axis like this, another e to the x like that, this actually goes through.
So it goes past 1.
Yes, yes. This is never undefined. 1 over e to the x is never undefined because it can never be 0 on the bottom. So what would happen is if I started to try and draw the sine curve, this sine curve would actually have to get squeezed between those two exponential curves. It's pretty cool. If you graph them all together, it looks pretty awesome. But all right, all you need to know, bounded over infinity, 0, done. You just need to state that somewhere. If you're doing the problem, like let me know that you recognize bounded over infinity, and then move on. Now the next type of problem that we need to be able to handle is this concept of infinity minus infinity. What would happen if we had infinity plus infinity? It'd be infinity, okay, but we don't want to look at that. We want to look at this. So your first example here, let's do one. Limit x goes to infinity of x squared minus x to the 5th. And for those of you who watch my homework solutions, there was kind of a rule of thumb that I said you could use for this. Whenever you see infinity and minus infinity, you always try and do what? Anyone remember? Factor. Factor out something. Try and get a common factor out. So look, yeah, you can pull an x squared out here. So I'm going to convert this subtraction into a product. So this becomes limit, but I'm doing some algebra, right? This is what you would consider algebra? Factoring? You agree with that? No, you shouldn't agree with that. Bless you. You should agree with that. So I now have a product here, and I know infinity, squared, that's going to be infinite. So I have infinity. This is headed towards infinity times, now tell me about this piece in here. Infinity cubed, infinite, 1 take away infinity, negative infinity, right? Negative huge number. And now when you multiply a huge positive number times a huge negative number, you would get a huge negative number. So negative infinity. Got it? So we always want to transform that into a product. That one was very straightforward. Give you another one that's a little more complicated. How about limit x goes to infinity? Let's do the square root of x minus the cube root of x. Kind of, yeah, but I think it was square root of x minus x or something like that, yeah. I put 2 roots in here for you. So there are actually 2 ways you could do this. One of them is to do like like try the conjugate thing, because you see roots, you start thinking conjugate. The other way is to factor.
Yeah, you can factor it out.
Yeah, so how do we factor this? Can you factor that? This is always where people have trouble, huh?
Square root x and 1, 12 out of
Yeah, it's a little tricky because one's a square root, one's a cube root, right?
Oh, so for the first one, it would be the square root of x to the third minus, because you do x to the sixth, you divided x to the sixth, you would have square root of x to the, no.
I'm with you. I'm with
You know
you.
what I mean, right?
I do. Let me
The sixth root, that's what I mean.
let me do it this way. How about I go to this good old thing that we had back in college algebra? How about we go to rational exponents instead of radical notation? Is that the same thing? X to the 1/2 means the square root. X to the 1/3 means the cube root. Agreed? Now, if I'm ever going to have any hope of putting these two together or having something that allows me to factor out, I'm going to have to get a common denominator. I need to look at both of those fractions as being the same denominator. So 1/2, 1/3, I can do, common denominator would be 6, right? So I could rewrite the 1/2 as 3/6. I could rewrite the 1/3 as 2/6. Agreed? I have not changed anything, have I? Okay, now I have to see what they have in common. And just remember that when I factor something out, like when I factored x squared out earlier, right? And I did what, 1 minus x cubed? When I multiply this back through, what did you do to these exponents when you multiply that through? You add them, right? So I need to pull something out of this so that when I add the exponents, I get both this and this back.
You can factor out x 2/6.
X to the 2/6. What do y'all think? Seem like 3/6 and 2/6 would have a common factor of 2/6? Let's try it. You could be wrong. Let's see. Let's try it. X to the 2/6. If you factor that out, how are you going to get x to the 3/6? X to the 1/6? Agree? I put those together, I get 3/6 when I multiply them, and that's 1/2, so that's good. And then x to the 2/6 right here, minus 1, right? Distribute that through, I get back this. Questions? Does that work? Is that going to work? I think so. Because now, this is really x to the 1/3, right? And so I'm taking the cube root of x. So if you plug in infinity, the cube root of infinity is going to be infinite still. Times now the sixth, whoa, the sixth root of, the sixth root of infinity. I told you my other class was making fun of my voice, right? Or was it this class? It was my other class, okay. You give me a hard time. All right, sixth root of infinity would be infinity, right? Minus 1, still infinity. So you have infinity times infinity. So it's infinite? Yes.
Can't you just kind of look at this though and intuitively know that the square root of x is going to be
Yes, you can. And we could have done that with the previous one also, right?
infinity? It's not going to be negative.
I agree. So, what's your name? Laura. Okay. So Laura's pointing out that, look, like the previous problem, right? It's kind of obvious that this term dominates, right? As x gets big, this is a dominating term. So this should be bigger. So we should get negative infinity here. And here, the square root versus the cube root, right? Which one is going to make a smaller number? This, when you cube root, it's going to be smaller than this square root. So yes, I agree with you. You can. What's more important here is the algebra that I'm doing here will creep its head out later on, and we just want to be comfortable with the algebra. So on the test, I need to see the algebra. Yeah. But your intuitive answer should match what you get algebraically. Okay. And that's it. That's it for wrapping up that section.
So here, infinity minus infinity, there's only two answers.
Infinity minus infinity.
It's only infinity and negative infinity, or is there?
No, you could get something else. It could happen that there's a balance. There's only one limit that we have that we guarantee 3 possible answers: infinity, negative infinity, and does not exist, and that's the fixed over 0. Infinity minus infinity, I'm trying to think of an example right now. I can't think of one right offhand, but I'm sure I could find something. Yeah, I'll think about it. Okay, we good? Chapter 1 is done. All right? Our test is a week from today. It's a week from today. It's going to cover all of Chapter 1, 2.1, and 2.2 is the plan. Let's see how today and Thursday go. All right? We'll talk a little bit more about the exam, but I'm really not going to, there's not going to be some big formal review where we're going to spend the whole day doing anything. It's just, study your homework, go back, look at the lecture notes, look at the course videos, look at everything, study, practice, come in, take tests. All right?
Any ballpark, how many questions you're going to be?
No idea. I haven't made it yet, so I don't know yet. I'll try and give you some guide, some gauge.
This is not going to be like 100 problems.
It's going to be 300 problems. 300 problems. All right, so today is chapter 2, which is called differentiation. And we're starting with 2.1. And I trust that all of you watched the video. It was very entertaining. I know how entertaining they are. So there are 2 major concepts that you have to take away from this video. The idea is that we're trying to find the slope of the tangent line to a curve at a point. Right? That's the theme. So given a curve, we pick a point A. There's that point. It has the coordinates A, f of A. And then I need to somehow slide this point over until it lands right on top of that point. And as I do that, I will generate the tangent line, which is right there. Voila, we have it. And that's what we're going after. 2 things, the slope of it and then the equation of it. Those are totally different. Well, they're connected, but if you're asked for the slope of the tangent line, that's one thing. If you're asked for the equation, you have to do more work. So we want to do that. How many formulas are there to do that? There's 2 formulas. And you need to know them. You need to know them. So here they are. Let's see. Let's see if anyone can impress me here. Anyone want to give me one of them without looking at your notes?
Mine is
No, I'm saying what I want here is the formula for the slope of the tangent line to a curve. Limit as h approaches 0, okay? F of a plus h minus f of a all over h. Okay, that's one of them. And the picture that we have that goes with this is that you have a function f, you pick some point A, you pick some other point to the right of it, which is that point plus something, which was that point plus h. That gives you a second point. Rise over run, right? That looks flat, sorry. Rise over run, this is the formula you get when you do rise over run. And to move the point on top of the other one, to slide this one over, we make this h, which we're adding to the a, we make it smaller and smaller and smaller. So basically we let h go to 0. So that's one of them. That needs to be hardwired. And in fact, this one is the one we will use most often as we move out of this section. So that one for sure you should know. The other one, and do these 2 formulas give you different answers? No, they give you the same exact answer, it's just different picture, but you get to the same place. So let's see if anyone remembers this one. No? Here, let me draw, how about I draw the picture? Okay, maybe we can get it if we draw the picture. Here's the point A, Here's the other point, and I don't say a plus h, I say x here.
So f of x, or f of x minus f of a.
Good, that's the difference in the y coordinates, so that's your rise over
Or x minus a.
x minus a, that's your run, and then what about the limit? How are you going to move this point to that point?
That point.
X needs to approach a. Those are them, right there.
These are both for the slope?
These both give you the slope of the tangent line.
Although on the note it says 0
Where?
on your online notes.
You sure you weren't looking at the H one?
Positive, I go double.
Well, okay, please double check, because that would be a typo. All right, what was your, these are both the same to give you the same answer. They give you the slope of the tangent line at the point A. So it's at this point right here. Right there, slope of that line, right there, slope of that line is given to you by that formula. Okay? That's what the entire 2.1 is about. So what we need to do is practice, do some problems. See if we can come up with the slope of the tangent line. And then, after we come up with the slope, see if we can come up with the equation of the tangent line.
Those situations just keep whatever one you feel more comfortable with, or
Well,
situation you don't use.
you know what? You should be able to use them both in terms of, what I mean by that is they should both work. A lot of times the algebra of one formula is easier than the algebra involved in the other one. And the only way to really know that is to, after you've worked like a couple of 100,000 problems, you start to recognize, oh yeah, no, I'm going to use this one instead of the other one. So we have like the h goes to 0 formula versus the x goes to a formula. You just kind of see the differences in when you plug things in, like how things are going to look. But let's do some examples and then we'll contrast. The first few examples I do, I'm going to do both. I'm going to do using both formulas so we can see the difference in the algebra and also confirm that we get the same answers, right? So let's, normally what I do in my lecture videos, or in my lectures, is I do some of the homework problems, but I've already done videos of the homework problems, so I'm doing other problems. So I'm going to do, I think the first one that I want to do is a cubic one. Yeah, let's just start with this. So if f of x equals x cubed minus 3x squared plus 1, find the equation of the tangent line at 1, -1. So geometrically, I have this third degree polynomial, right? And if I go out to it somewhere at the point 1, x1, I should be at this point on the graph. And then the graph, I don't know what it looks like, okay? Well, I kind of do, but I don't know where everything is, right? And where the turns occur, I don't know. But I'm trying to find on that curve, let's just say it did this. I'm totally making this up. I'm trying to find the slope of the tangent line there, and then use that to come up with the equation of the tangent line. And when I'm done with this, what I'm going to do is I'm going to go to my computer, I'm going to graph this, and I'm going to graph our equation, and they need to match up perfectly, right? This line that I draw should go through that graph at that point, and it should look tangent. So we'll see. All right. Let's start by finding the slope. The slope of the tangent line will be equal to the limit, and now my choice. So let's start with the h goes to 0 one first. And in college algebra, you spent a lot of your time doing this thing called a difference quotient. And sometimes it was presented that way. And you practice doing it in college algebra so that when you got to this class, you would be used to the algebra required. And now we're putting a limit in there. That's the only real difference. All right, so let's see, what does it mean to plug a plus h in? Well, do we know any of these things? Do we know, like, can we replace any of this up here? Yes, the a, right? The a is what? The a is the x-coordinate of the point we're looking at. So this point right here is a, right? That's a. And we also know what f of a is. F of a is -1. And that's because if you plug this a into the function, it needs to spit out this value. So this is the function's value at a. And let's just double check it because I made this problem up. If I plug in 1, 1, yeah, it should be -1. So it works, right? Okay, so let's rewrite the formula now. This is the one I have memorized, and now I'm going to replace a with 1. That's not replacing a with 1. That's writing a again. 1 plus h, and then minus f of 1. I'm going to replace that with -1 on my next line. Okay, this is 1 being plugged into the function, which I'm about to replace with this. My next line is limit. Notice my limit's coming along for this ride the whole time, right? I'm not forgetting it. I'm going to keep writing it all the way until I actually take the limit. Now, college algebra, evaluating a function, plugging something into a function. 1 plus h must be plugged in to this function. Everywhere you see an x, it gets replaced with 1 plus h. So it's going to be 1 plus h cubed now. What do we got? Minus 3 1 plus h in parentheses there squared plus 1.
Then minus the f1, which is the -1.
Yep. So we've only done up to there, right? We've only done this top left corner. Now we need minus. Now what's f of 1? -1. So minus a -1. That's it, right? That's the whole numerator? All of that over h. And our goal is to make an h cancel, okay? Because just like we did back when we were doing limits before this, is that we always wanted to get rid of the thing that was going to cause the problem. Right now, if you take the limit, okay? If you come in here right now and take the limit, you are going to get 0 over 0. You do not have to check that. It's guaranteed. I mean, this is always going to give you 0 over 0, always. So now we need to do some algebra. Here we go. Limit. I write it again. H goes to 0. And I'm going to expand 1 plus h times itself. Again, right? 3 times 1 plus h times 1 plus h times 1 plus h. I believe on the homework video I do actually do it by hand for you. So for today I'm just going to write down what it is. Pascal's triangle, which I will talk about. I'm just not ready yet. 1 plus 3. Really? I will. There is a time. There will be a point coming up soon where I will be forced to talk about it. So that's when I'm going to get into it formally. That's what we should get if we expand this. And then we have minus 3. And then I have to expand 1 plus h, right, squared, which would be 1 plus 2h plus h squared. And notice that has to be in parentheses, right? Because the -3 must distribute to whatever these two whatever these two factors multiply to be. The -3 must pass through. And then, what do we have? Plus 1. Plus 1. Which is 2, yes, I know. But we'll get to it. H. What should I do next? Distribute that -3 through? Now look, if you can do all that mentally, like if you could have done this in your head and then distributed the 3 in your head, that's fine. I don't care. trust me, there are some calculus classes where all the instructor does is put this in, and then the next step shows it all simplified. I understand that this is where most people get hung up on this algebra part, which is why I spend a lot of time on it. All right? So if you have questions, you need to ask. If you're unclear on any of this, that's why I'm here. That's why you're here. Can I just put +2 finally? All over h. When you do your homework from this point on, your hand should hurt when you're done. Okay? I mean, you're going to do a lot of writing. All right. If you've done everything correctly, everything should cancel with the exception of terms that have h's in the numerator. All right, so I'm going to start canceling things out. Let's see. I have a 1. I take away 3. I add 2. That's 0. Gone, gone, gone. Anything else that doesn't have an h in it that can go away? I don't see anything going away. I do have some like terms, though, don't I, that I can combine? Let me combine like terms. Equals limit again. Hello, see? Don't forget about it. 3h, do I have any more h's? Yes, minus 6h. So negative 3h. And I've taken care of those. These, I'm not saying these cancel. I'm just kind of checking them off. I've already done those. 3h squared minus 3. Oh, those did cancel, didn't they? Those were gone. And then there's just an h cubed. So plus h cubed over h. I will write the limit again because I'm not ready yet. This is my first example, so I'm going to factor an h out of the numerator. And there I get my cancellation. Still going to write the limit. Limit h goes to 0 of negative 3 plus h squared. And now finally, you let h go to 0 and you get negative 3. What does that negative 3 represent?
Is that when you get really close?
That's right. The slope of that tangent line at that point is negative 3. So I know it's actually pitched down pretty steep, right?
So the next step between algebra and calculus with this particular is
Letting h go to 0.
Yeah.
That's it. That's it. That's why if you can't do the algebra, you can't do this, right? All right, so we have answered the question?
no, we haven't done.
No, all we've done is found the slope. What did the problem say? Find the equation of the tangent line. So now you have to go back to college algebra again, and you have to remember the formula that we used to find the equation of a line. See, the tangent line will always be a line. And there were multiple versions of equations for lines. One of them was this one. This is one we really liked using. We really loved that formula for a line. This is called the slope-intercept form of a line. It's very convenient if you know the slope of the line and you know its y-intercept, right? We know the slope of the line, but we don't know the y-intercept. There was another formula that we used for that one, which was this. This was called the point slope formula. It's what you use when you have a point on the line and the slope of the line. We have the slope. We also have a point on the line. What's the point that must be on the line? The point that's on the curve, right? 1, negative 1. So all you have to do at this point is go into this and use this information. This is what we know. We know the slope is negative 3. We know that the point x1, y1 is the point 1, negative 1, right? And just replace. So y, and then I'm going to go what? Minus negative 1, which will be plus 1, equals negative 3, and then in parentheses x minus 1, like that. And then y plus 1 equals negative 3x plus 3. That's me distributing through. And at this point, you could argue that you've answered the question. That is an equation of a line, isn't it? It's just not in the form we like to put them in, which is solved for y. We like to get y by itself so that we can graph it easier. So I'm just going to subtract 1 on both sides. All right, there you go.
Although in the notes you left it in that form.
Yeah, in the notes I did?
Yeah.
Okay. Yeah.
Or
All right.
at least the form was in that.
Which would be a correct answer. So now the moment of truth, okay? I haven't worked this problem out, so I'm going to put myself on the spot here. Do you think we got it? I feel good about it. I'm just going to go, I'm going to use this program called WinPlot. This is a free software. It's very, very archaic. And I'm going to have it graph, first of all, the original function, which was x cubed minus 3x squared, tell me, yes, plus 1?
Plus 1.
Okay, and I'm going to lock that interval. I'm going to go pen width of 3, and there, oh, whoa. No, don't lock the interval. Try that again. All right, there's the graph of our polynomial function. And now I'm going to have it graph this. I'm going to graph this line now, okay? What should happen? What should I get here? I mean, what am I looking for?
At 1, negative 1.
At 1, negative 1, right here, right? At this point, I should have that line that I graphed should pass through that point and look like it's tangent to the curve. The fact that it's a negative slope makes me feel good. So here I go. I'm going to graph negative 3x. What was it? Plus 2?
Yep.
Plus 2. And I'll make that one this. There we go. Looks like it. Okay. I'm going to go even further. On this program, you can actually have it graph the tangent line. Where is it? Slider, I think. Tangent. Base point. I don't know if y'all can see it. See that flat line up there? That's the tangent line that the computer graphed because I told it to go to 0. But I want to move that out to an x value of 1. So if I do that, it just moved it. You can't see it, can you?
It's on top of
It's right on top. So I'm going to take my other one. I'm going to, where's the hide? I thought there was a hide there. Oh, there we go, graph. So I'm going to take it out, gone, right, hidden, bring it back, right on top. So we got it. Do you understand geometrically what we're doing? Everyone clear? All right, let's do the same problem. Let's use the other formula. We'll take it all the way to the point where we get negative 3 again, but we're not going to go through and write the equation again. We're just going to get to that slope being negative 3. So I'll write down the function again. X cubed minus 3x plus 1. This time the slope of the tangent line will be equal to the limit as x approaches a of f of x minus f of a over x minus a. That's my formula this time. Can I replace anything in this formula?
Yeah.
Replace what?
The A.
The a is 1, right? The a is 1. Just like in the last one, the a was 1. So I'm going to just go and rewrite this limit. X approaches 1. F of x doesn't change, but this turns into f of 1. Then over x minus 1. See that? Just replace that a with 1, that a with 1, that a with 1 right there. And now we're ready to go.
Is it the bottom one negative one?
Uh,
Or one of them is negative one?
what was A? A was 1, right? A was 1. So the formula is x minus, right? A, if A is 1, it's just going to be minus 1.
So wouldn't f of a be -1?
Oh, yeah, I'm sorry. I thought you were saying, okay, yes. So now what I'm going to do is I'm going to actually replace this with whatever it is, and replace that with whatever it is, and then see what I've got. So this becomes limit x approaches 1 of, what's this? Well, f of x. That's just the function, right? All you have to do is copy exactly what you see right here. So x cubed minus 3x squared plus 1. Wasn't that easier than what we had to do in the last problem? Last problem we had to do the expansion of 1 plus h cubed. And that, you know, that was pretty easy to plug in. How about this? Minus f of 1. F of 1 we said was -1, but you're subtracting. So plus 1. All over, not h, right? X minus 1. If you take this limit right now, what should happen? You should get 0. You would, okay? 0 of 0. So we have to do some algebra. Limit x goes to 1 of x cubed minus 3x squared plus 2 over x minus 1. So far, this looks a lot nicer, doesn't it? So far? What do we need to happen in order to get around this whole division by 0? What do we need to happen? X minus 1 factor on the bottom has to cancel. Like in the previous one, we needed the h to cancel. Here, we need this to go away, the whole thing. Okay? So, any ideas?
Factor the top.
Factor the top. How? That's not a quadratic.
Oh, long division.
Long division or synthetic division. Correct. That's the way. So if you're going to have any hope of factoring this, you need to remember how we can use synthetic division or long division from college algebra to factor. So at this point, you might be saying, yeah, maybe the other way was better. It depends on your comfort level, right? How comfortable are you with that? So here's what I'm going to do. I'm going to use synthetic division because it's a faster form of division. What I'm going to do is I'm going to say, does this divide into this? Does it? Let's see.
That's why I said do long division, because I didn't know, you know.
Oh, I'm doing this. That was long division, sorry. I'm going to do synthetic, yes. So what are the things I put inside here? 1, -3, careful, 0, 2. So we're putting the coefficients of this, and then we're trying to divide by this linear expression. Drum roll, what number goes out here? What is it? Plus, okay, yes, plus 1, positive 1. Positive 1. You do the opposite of this number here. And now you do synthetic division, which if you don't remember, you might have to, just go back and review it. Okay, we drop our 1 down. You multiply 1 times 1, that gives you 1. You place it underneath here, so we're doing this thing. Then add down again, you get -2. What are we hoping for at the end? 0. 1 times -2, -2. Add down, you get -2. 1 times -2, -2. And you get 0 here. And that's what you need in order to say it divided. Okay? Now, this definitely, this is going to depend on your instructor. All right? This next part. What I teach my students in my class is that we use this table to rewrite the polynomial. When you say that this thing right here can be divided by this right here, that means that this numerator can be rewritten using this information. It can be rewritten, first of all, we'll do this. Using those 3 numbers, this becomes 1x squared minus 2x minus 2. So you always start off, these are the coefficients, and the power here is always 1 less than what you started with. So if that were x to the 4th, this would be 1x cubed. So it's that times, and then I use this number here, and you take the opposite, or you can just say it's that right there. So I know that this is, the numerator actually factors. What I've done is I have factored the numerator. So this becomes limit x goes to 1 of x minus 1 times x squared minus 2x minus 2 over x minus 1. And then the two factors cancel, and we're there. We just let x go to 1 now. So let x go to 1 right here. You get 1 squared, that's 1. Here, minus 2. Here, that's just minus 2. And this gives you negative 3. Check, that's what we got last time.
A little quicker.
It's just going to depend, again, if you are not comfortable with synthetic division or long division, you'll be going with the other one, right? Questions?
Although I suppose if you didn't know that x minus 1 came out of there, that you'd have to do long division.
Well, you know what? We know it does. And here's why we know it does. The comment was, we don't know if x minus 1 actually goes in there. It guaranteed does, because when we plugged in 1, right, they both were 0, right? And if I plug 1 into this and get 0, that means that x minus 1 is a factor, guaranteed. That's the, yes?
What if you get 1 over 0? Does that mean the limit won't exist?
If I got 1 over 0, while we're trying to find the slope of a tangent line, you've done something wrong. You're always going to get 0 over 0, because the formula, right? The formula itself guarantees it. This guarantees it, because if I replace x with a here, the top is 0, the bottom is 0, always. So if you get something other than 0 over 0, something in your plugging in went wrong. Any other questions? All right, let's keep going here.
Is there one method, I guess, more useful than the other, or just really depends?
The h goes to 0 is more commonly used as we move forward. We'll be using the h goes to 0. But see, what's going to happen, for those of you who already know what's going on in this calculus class, is that at some point we will be doing this, finding the slope of the tangent line with a shortcut. And we're just going to put the limit away. And you'll be mad about it, but you'll get over it.
Because I'm sure this will come in.
Well, I said in the very beginning, the limit is the heart of calculus, and to not get a good exposure to limits would really handcuff you as you go through and do more mathematics, because you need to be comfortable with the limit. The limit never stops in mathematics. It's always there. So anytime you do math that doesn't have limits, it's pretty basic level math. It's finite math. It's just compute, calculate, end of process, done. The limit is like you're letting something approach. It's an infinite process. That's where math becomes interesting. All right, we need to do another one. We need something ugly, right? Okay, how about this? Let's do find equation of tangent line to the curve f of x equals 2x over x squared plus 1 at 1, 1. Or let's make it negative 1. Negative 1, negative 1, negative 1. Okay, yeah. If I plug in negative 1 here, I get negative 2 over negative 1 squared 1. 1. Yeah, that should be. Okay. It's squared. Negative 1 squared.
Right.
All right, everyone understand what we're supposed to do? All All right. Slope a tangent line first. Your formula, your choice. Go ahead. I'm going to let you start with it. Just at least write the formula down, start plugging things in. While you're doing that, I'm going to cue something up on the computer. But I want you to at least start with the, and you get to pick whatever you want. Sorry. Okay. I want you to, you work. We're going to watch that in a minute. Real quick, h goes to 0. Raise your hand. Who's using h goes to 0? Okay. Who's going x to a? So we got about an even split here. This ought to be interesting. So I didn't want you to go too far with it. I want you to get it at least set up. Does everyone have at least everything plugged in?
Oh, I was already.
Just, yeah, it's okay if you've already solved it. I want to make sure everyone's at least to the point where you got one of those two. Yes? Does anyone need help getting to that point? Yes? Which one are you using? H to 0?
Yeah.
H to 0. So you're using limit h goes to 0, f of a plus h minus f of a over h, right? Which for us would be limit h goes to 0, f of negative 1 plus h minus f of negative 1 over h. So replacing a with negative 1, a with negative 1, right? That's good. Plug negative 1 plus h into the function. So here's your function. Replace that with negative 1 plus h, 2 times that, over, replace that with negative 1 plus h, plus 1. Got it?
No, okay, yeah.
Then subtract from that f of negative 1. F of negative 1 is negative 1, so I'm subtracting negative 1. So wherever my h goes to 0, people? H goes to 0? Anyone else need help getting to this step? This is the time. No? How about my x goes to a, people? Everyone okay with this? Any questions on that? No? I wanted everyone to look at these and decide which one they think would be better. I thought we might take a vote as a class.
Honestly, if you're doing all division,
Let's talk about what we would need to do. Let's do it this one, because I think this one looks cleaner. Looks cleaner, doesn't mean it's going to be. Okay, what would you need to do here? I mean, I could switch this minus, right? Minus minus.